So today we're going on from homeostasis and moving on to the action potentials and synapse in the body, which are inside of the nerves in your brain that helps give signals to the other organs in your body so that so they'll know when something is wrong, or like if you feel pain somewhere, it sends the signal to the brain and then it goes back to the organ, so it tells you where the pain is and where it may just where the pain is. And so we're going to first talk about the steps of action potential and the functions that go into causing the action potential in the neuron. So let's get started. You guys, so first, instead of just jumping straight into learning about the action potential, we're going to review what a neuron looks like and where the action potential will actually start. So the neuron just starts the signal up here and it travels the signal all the way down this axon to get to the axon terminals to transfer the signal to the next neuron. So actually the action potential starts in between this right here so that the signal can travel and get transferred to the next neuron. So first we're going to start about where the action potential starts and what happens during this stage. So now we're just looking at a blank a blank membrane of the inside of the neuron where we were talking about the axon. And so the parts that go into making up the neuron are the channels that transfer all of the molecules from one side, from the inside of the neuron to the other side, to the outside of the neuron. So the only two molecules that we are using are Na plus channels and K plus channels. And if you don't know what Na is sodium and K is potassium. So now we're going to add pumps to the membrane so that when they have to travel back and forth, and they don't have to keep constantly using this same channel. So when these channels are universal, so Na and K plus, Na plus and K plus can travel through these pumps right here. So now, in order to figure out what to do with the molecules and where the molecules go, you have to, well, not in order to figure it out, but just to know that K plus or potassium goes in the inside. There's like a lot of potassiums in the inside. And the sodiums go on the outside of the molecule of the of the neuron or the membrane. But occasionally there will be some that will go like on different spaces. So like sometimes some K plus will be on the outside. It's not going to be a whole lot, but it's just going to be some that will be on the outside. And there will be like occasionally like one Na in the inside of the neuron. Oh, we're going to put this one right here too. Inside the neuron. So in order to remember the colors, I've put a key right here that states that Na is orange. Sodium is orange and potassium is yellow. Okay, so now we're going to talk about the first step of the action potential, which is the resting membrane potential. And then in this period, it's just starting the process of sending the signal into the next neuron. So during this stage, all the channels are closed and all of the gradients are still there. And well, gradients are just the way to keep all of the molecules that are supposed to be on the same side. So there are sodium gradients and potassium gradients. So that just lets them know to stay on the side they're supposed to be on. So it just tells the sodiums to stay on the outside and the potassiums to stay in the inside. Okay, now we're going to move on to the next stage, or the second stage of the active potential, which is depolarization. So in this stage, the sodium channels will open, and now the sodium molecules will be able to travel inside of the neuron. So there's going to be a couple that go inside and a couple that stay where they are, and some will go just inside the neuron. And yeah, inside the neuron. So they'll all be inside the neuron. And now that means the sodium gradient has been eliminated, and that what makes all of the sodiums be able to go inside of the neuron. And so that causes the graph to go to plus 40 MVs. And if you're wondering what I'm talking about, a graph, I will show you now. Okay, so this is the graph that I was talking about. So when you're looking at the graph, this is the resting period potential. So this is the resting membrane potential, and this is the threshold that the graph will go to, and this is the plus 40 MVs that I was talking about. So this side is the membrane potential, or the MV, and this is the time that it takes to get to that part of the graph. And so get to that time, how long does it take that period in the active potential to go, or how long will it be? If you get what I'm saying, I'm trying to say it without getting myself confused and you confused, but it's kind of like, how long does it take for that period to last? That's what I'm trying to say. Okay, so first we're going to draw the resting potential, the resting membrane potential on the graph. Okay, so I've drawn the resting membrane potential. So it's just staying at a constant negative 70 MVs. Oh, I forgot to say that. Okay, so when you're at the resting potential, it is always a negative 70 MV. Okay, and so now if you wanted to draw depolarization goes to plus 40 MVs. So now I'm going to graph that. Okay, so for depolarization, it goes up. So you draw a line from the resting potential all the way up to plus 40 MV, which it surpasses the threshold. So it means that it's going over that point on the graph. So now we're going to talk about the next stage of the active potential, and we're going to figure out what happens with this graph afterwards. So the next stage of the action potential is repolarization. So repolarization is just the system, or the period where the sodium channels will close and the potassium channels will open. Okay, so now this means that the sodium gradient is now reestablished and the potassium gradient is no longer available, or it's been eliminated. So now all of the potassium molecules will be able to travel outside of the of the neuron. Okay. Oh, and we're going to take one more onto this side. Okay. So now, and to know what happens on the graph of for the refractory period, we're going to look at the graph to understand what happens. Okay, now so looking at the graph, we know in the refractory, so now I'm going to tell you what happens with the graph in the refractory period. So for this one, it is kind of not on the graph, but it goes down. It doesn't keep increasing. It makes that curve and then it goes down like a hill for the refractory period. So I'm going to graph that now so you can see what I'm talking about. Okay, so I just realized while I was graphing this that I said refractory instead of repolarization, which all the times that I said refractory instead of, if I said refractory instead of repolarization, then I meant repolarization. So now we're going to talk about the repolarization on this graph. So like I said, it'll go, it's kind of confusing, which is not actually a number on the graph, but it goes below the threshold and it goes below negative 70 MV. So it just is going to decrease and decrease, and it's going to go below negative 70 MVs. And so now we're going to talk about the next step, the very last step of this action potential process. Okay, now we're going to talk about the last step, which is the refractory period. We're finally getting to the refractory period. So in this period, all it's trying to do is get back to its normal state, or the state that it was before the action potential started. So at the beginning of, so we're getting back to the resting membrane potential. So this cycle is just the circle of life, and it just goes around and around. Like I said, like Mufasa said in The Lion King, it's just the circle of life. And so now we're gonna figure out what happens in this period. Okay, so in this period, all of the channels were closed and all of the gradients will be established. So there now is a potassium and a sodium gradient. So now we're going to figure out, now you're probably wondering, how are the molecules going to get back to the side they are supposed to be on? And if you remember from the beginning, I said these pumps right here were universal, and that they would take out sodium and bring in potassium. So now we're going to use these pumps. So these pumps will take out 3 sodiums. 1, 2, 3. We'll take out 3 sodiums, and then it will take in 2 potassiums per pump. So it'll go in 2. And now it's back to the state that it was at the resting potential. Now we're going to look at the graph and figure out what it would look like on the graph. Okay, so by looking at this graph, to get through the refractory, to show the refractory period, the refractory period is just the state where it's trying to get back to the resting potential, or the resting membrane potential. It doesn't matter which one you say, but it'll still give you the right answer. But so this period, the refractory period, is going to get back to negative 70 MV. So it's just going to go up here, and it's going to go straight across, and then it's going to do the process all over again. So I'm going to graph the refractory period now. Okay, so now you can see what I was talking about, where it is going to go back up and go straight across the negative 70, because it's getting back to the resting potential, so it can start the process all over again. And so the action potential process has just made the signal go all the way down to the axon terminals at the end of the neuron. And so now we're going to move into the next step, so that the signal can get transferred to the next neuron, which is called the synaptic process. So now we're going to look at the synapse, or the synaptic process of this. And so now we're going to move on from we're still going to have sodiums, but now we're going to have calciums. And so now we're going to move on to the other parts of this process. This process has more parts than the other process, but it's the only way for it to get the molecules and the signals to the other side, or the other neuron, so that it can just keep traveling down until it gets back to the organ that it's supposed to be. So this is the axon terminal. So this right here is the axon terminal of the other neuron, and this is the dendrite of the next neuron. So it's going to travel is gonna, all of those, the signal is gonna go from here to here. Okay, so the first part of this process is that the sodium molecules will travel inside of the neuron. And so you're going to have NAs, you're going to have some NAs inside the neuron. And so then that's going to make these calcium molecules go inside the molecule. It's also Ca2 plus Ca2 plus. Okay, so once these are moved inside of the neuron, these vesicles will dump out the neurotransmitters. So these green, I call them, they look like green squares. So the green squares inside, they're going to dump them, we're going to take them and dump them into the synaptic cleft or the synaptic gap. So we're going to just look at it if it was just dumping out one of the vesicles. If we're just looking at if it's dumping out one of the vesicles. So the neurotransmitters dump out, the vesicles dump out the neurotransmitters, and they move over to the ligand-gated receptors. And so now it will open, the neurotransmitters will go into the ligand-gated receptors, or if you want to just look at it like they look like this, they look just like that. And so the neurotransmitters, they go in like a key, and so they just go in and then they open after the neurotransmitter opens or connects to the ligand-gated receptors. The Na molecules that are still on the outside, because sometimes they're still on the outside of the molecule, they go inside the next neuron. And so that's the next part of this. Well, this is where the signal is being transferred to the next neuron. And so once this Na plus is transferred inside the next neuron, the neurotransmitter will leave or disconnect from the ligand receptor, and the receptor will close, and Na is still on that side. And so, okay, we'll flip it on this side because I had it on the wrong side. Okay, so this is what it would look like, not the other way. But, okay, so we're going to look at it like this. And so, the same process, but now we're going to get to where the neurotransmitter, it goes back through the reuptake pump. The reuptake pump. And it goes back. They are reused and they are recycled in the vesicles. Like I said, the neurotransmitters will go up the reuptake pump. They'll go back inside the vesicles. The vesicles will go back around the neurotransmitters, and then the cycle will repeat itself. Okay, so now we're going to look at, that was the inhibitory process. The inhibitory process is the same thing. It's just that chlorine or Cl minus will go inside of this and not Na plus, I think. Yeah. Okay. So now we're going to move on to a different concept of this same synaptic process, but it's if you was taking a drug. So in this case, we're going to use cocaine. So this is the picture we was looking at previously. I just had it on the wrong side. So it's the same process. The neurotransmitter will go to the ligand-gated receptors. The Na plus molecule will go inside. Then neurotransmitter will leave and it'll go back to the reuptake pump. But instead of it going inside of the molecule, it can't, because there are these blockers that are covering the end of the reuptake pump, and that makes the neurotransmitters say, oh no, I can't get in there, I can't enter. And so now, instead of going back, it will go back to the ligand gated receptor, and it will keep opening and closing and letting NAs inside. And so we're going to look at it like this. And just say we had multiple of these, because there's are hundreds of these just lined up on the outside of the neuron. And so because the neurotransmitters keep opening and closing and letting all the NAs in, that's what makes the people feel so happy when they take the drug, and they just want to keep taking it, keep taking it. And so then it will make these disappear because they're being over processed. And so that will just keep making those, they'll keep going on around the line, and then they'll just keep disappearing. And until you get medically, or until you get unaddicted to that drug, that's when they'll start going back. And that's what's the withdrawal process. And so that's why when people are in withdrawal from the drug, that is because their ligand gated receptors are trying to grow back, or grow back and start the process, the correct process of the receptors, of the synaptic process. Alright, you guys, so I hope you learned something from this video, and I hope you have a good day. Bye.